Hey everyone, so this is the solution video for Worksheet 3.2. We're going to be talking about polynomial long division, and specifically we're going to get started with a few examples where we're going to be taking some polynomial and thinking about how we can rewrite it or break it down into smaller pieces. Specifically, as it says here, we're going to take some original polynomial p of x. So this p of x sort of represents the original polynomial or some polynomial function that we want to break down in some way, shape, or form. We can break it down using long division as a function d of x, which is essentially our divisor, what we're going to be dividing into it, as we'll see with some examples, times this q of x. This q of x represents a quotient. And if you remember, the quotient, the term the quotient refers to the result of dividing some number into another, or in this case a function into another function. And then lastly, we may be left over with this r of x, which is our remainder function. And sometimes we have a remainder, sometimes we don't. And we'll see that in this video. So this is what we're trying to do, is we're trying to break this down. The way that we do this is that we start off, and we can kind of get a preview with part A. We're taking this polynomial 2x plus 1. So this would represent sort of our p of x. And we're going to try and break it down by dividing into it x minus 3. So this would be our divisor, or our d of x. And in general, the way that this is going to pan out is the first thing we're going to do. So step one is going to be, we're going to take p of x and divide it by d of x. So we could set up sort of like a long division, and we've got our d of x function, or divisor, and we're going to divide it into whatever our polynomial function is. Now, what's going to end up happening through all of these steps is we'll get some quotient up here, which we call our q of x, and through a lot of steps down here, eventually we'll get down to our remainder, if one exists, and this will be our r of x function. So, and then these four pieces are then put together to come up with our polynomial, rewritten in a way that we can use to our advantage in some cases. So let's go ahead and try this with part A. So I'm going to go ahead and we're going to take x minus 3 and divide it into 2x plus 1. So we'll start off with the first step of setting up the long division problem. So we're going to take x minus 3, and we are going to divide this into 2x plus 1. Now, the first step with polynomial division is we want to take the first term of our divisor, and we're going to divide it into the first term of our polynomial function p of x. So I like to kind of put a little calculation off to the side. I'm going to take 2x and divide it by x to get started and see how this simplifies. And in this case, this is just going to simplify down to 2. So I'm going to take that 2, and I'm going to put it above the constant term, the one that it matches in our long division. Now all we have to do is take this 2 and multiply it through to each of these terms. So I'll take 2 times negative 3, which is going to give us negative 6, and then 2 times x, which is going to give us 2x. Now, once we've distributed that first term in our quotient back through our divisor, we're going to go ahead and we're going to subtract both of these terms from the term above it. So if I subtract 2x from the term above it, which is 2x, that's just going to give me nothing. It's going to cancel out. So that's just sort of a little 0 there, or a null. And then if we subtract negative 6x, that's going to end up giving us a positive 7. Now, at this point, we're going to stop. And the reason that we stop is because the next step would be to take 7 and divide it by x. But since the power of x is greater in the denominator than the numerator, we're just going to stop. So this is where we sort of stop. And this now becomes our remainder. So this is our remainder. And we'll see, where to stop. There wasn't really any more for us to do in this case. So let's see what we've got now. If we sort of take stock of each of these pieces, we see that, okay, so our original function, the p of x, was the 2x plus 1. Our divisor, or our d of x, was the x minus 3. Our quotient, q of x is actually this 2, because it's the only term that's left. So our q of x is going to be 2. And in this particular case, we do have a remainder, r of x, which is just 7. So we're going to take each of these 4 pieces, and we're now going to sort of put it together in the manner that they asked us to do at the start of the problem. So if we want to write this as p of x is equal to d of x times q of x plus r of x, what we're going to get is we're going to get that 2x plus 1 is in fact equal to x minus 3 times 2 plus 7. So this is just telling us that if we wanted to rewrite this term, 2x plus 1, an equivalent expression for that would be this right here. And the nice thing is that we can actually check this. So let's go ahead and do that off to the side here. So let's check. And to check, all we have to do is just take this new expression, multiply it out, and see if we get what we started with. So we take the x minus 3 times 2 plus 7, and if we distribute if you multiply this out, we'd end up with 2x minus 6 plus 7, which is equal to 2x plus 1, which is equal to our original p of x. So this checks out. So this is the type of process that we're going to be going through for these long division problems. This is a pretty simple one. There wasn't a whole lot to do, but I think it's a good place to start. So let's try this with a slightly more involved one. So we've got 2x cubed minus x plus 1, and we're going to divide that by this quadratic x squared plus x plus 1. And again, we're asked to check to make sure that this actually worked out properly for us. All right, so again, what we see here is that this is our p of x, our original polynomial, and we're dividing it by this expression. So that's going to be our d of x. So step 1, we're going to go ahead and we're going to set up our long division. So we're going to take x squared plus x plus 1, and we're going to divide it into p of x. Now p of x, we've got 2x cubed. And now one thing we want to notice here is that we're skipping a power of x. We're going from x cubed to x. We don't want to overlook that, and we always want to make sure that we've got a placeholder there to fill any missing powers of x in either our divisor or our polynomial function. So what we're going to do here is I'm just going to fill that space with a 0 times x squared. And I mean, that's originally where the number 0 sort of originated from, is as a placeholder in positional notation. So we're going to use that in the truest sense of 0 as a placeholder to hold that spot open. And then we can just go back and continue through. So it's minus x, and then we've got the plus 1. And now we just go through and we do our division steps. So I'm going to take the first term of our divisor and divide it into the first term of our polynomial p of x. So that's going to be 2x cubed divided by x squared. This is going to simplify down to just 2 times x. So I'm going to go ahead and I'm going to put that up over the x. So we've got 2x. And now I'm going to go ahead and I'm going to distribute that to each of these terms right here. And if I do that, 2x times 1 is just going to give me a positive 2x. 2x times x is going to give me a positive 2x squared. And 2x times x squared is going to give me a positive 2x cubed. And as before, I'm going to go ahead and I'm going to subtract each of these terms from the terms directly above them. So 2x cubed minus 2x cubed, nothing. It's going to zero out. 0x squared minus 2x squared is going to give us minus 2x squared. Negative x minus 2x is going to give us minus 3x. And then what we're also going to do here is we're going to, at this point, bring down this extra term here, the plus 1. And we're going to repeat the process now, because we can divide x squared into minus 2x squared. So the next step here is I'm going to take my x squared, and I'm going to divide it into this first term of what we now have going on underneath this long division process. So I'm going to take minus 2x squared and divide it by x squared. The powers in this case are equal, so we can go through with this. And this is going to simplify down to just -2. So I'm going to take my -2, I'm going to put it up here, and then just like I did with the 2x, I'm going to distribute that to each of these terms in our divisor. And if I do that, I'm going to get -2 times 1 is -2. -2 times x is going to be -2x. -2 times x squared is going to be -2x squared. And now we take all of these terms and subtract them from the terms above them. So -2x squared minus -2x squared. It's going to cancel out, and that should happen every time. Otherwise, you've probably made a mistake somewhere. -3x minus -2x, so we're adding 2x to -3, so it's going to be -x. And if we subtract -2 from 1, that's going to give us a +3. Now again, notice the next step that we would think would be to divide the -x here by the x squared. But if we did try to do that, we'd have -x over x squared. And again, when the power of that bottom term gets greater than the power of that top term, this is a sign for us to stop. We've hit our remainder, and we're just going to go ahead and stop at this point. So this right here, even though it's a function of x, is our remainder function. So this is our remainder. So now we can go ahead and we can identify each of the parts of this process. So our p of x was our original polynomial, which was the 2x cubed minus x plus 1. Our d of x was our divisor, which was x squared plus x plus 1. Our quotient, our q of x, is this up here, what we have on top of our long division, which is just going to be 2x minus 2. And then lastly, our remainder function is minus x plus 3. And we can take each of these to get the final step, which is to rewrite p of x. So we know that p of x, 2x cubed minus x plus 1, should be equal to d of x, which is x squared plus x plus 1, times q of x, which is 2x minus 2, plus r of x, which is minus x plus 3. So this cubic polynomial can be rewritten and broken down as into those three terms in that manner. And again, we're asked to check this, so it's probably not a bad idea just to make sure. If we multiply all of this out, let's see what we get. This is going to be a little bit messier than the last one, but that's okay. So let's go ahead and check. And x squared times 2x, that's going to be minus, positive 2x cubed. X squared times minus 2 is going to be minus 2x squared. And then x times the 2x is going to be plus 2x squared. X times the minus 2 is going to be minus 2x. 1 times 2x is going to be plus 2x. 1 times minus 2 is going to be minus 2. And then we've got this minus x plus 3 hanging on the end here. So let's see what happens. Minus 2x squared, positive 2x squared, those are going to cancel out. Minus 2x plus 2x, those are going to cancel out. And what we're left with is 2x cubed minus x, and then the minus 2 and the positive 3 will combine to be positive 1, which is what we started off with. So this checks out, and we did it correctly. In terms of WebAssign, this is the way that they're going to want this written, in terms of breaking it down to d of x times q of x plus r of x. So this is definitely something that you're going to want to be careful with when we're doing the homework. Okay, so one of the things that we can use this for is to help us find zeros and to actually factor polynomials certain times. So I think this last example sort of illustrates that. In this particular case, we're considering we've got some polynomial p of x, which is a cubic. And if we're asked to find all the zeros or to try and factor it, it's not an easy thing. We don't, we've got a quadratic formula for quadratics, but, beyond that, it gets a little bit tricky, if not outright impossible. So in this example, we're actually told, so this is our p of x. This is our polynomial. This particular polynomial has a 0 at 1. So that's our c. Now, if we know that 1 is a 0 of the polynomial, there's a rule that says if x equals c is a 0 of p of x, then x minus c must be a factor. So this is sort of, underscoring this connection between zeros and factors with polynomials and functions. So because of that rule, we can look at this and say, well, since x equals 1 is a 0, it's a known 0, we're told that from the get-go, then this means that x minus 1 must be a factor. So that takes care of part A. Now, if we know that this is a factor, that x minus 1 is a factor, what we can do is we can use division to find the other factor or factors, very much in the same way that we do numerical division. Just as sort of as a side example, if you consider that 7 is a factor of 35. The way that we could find the other factor is we take 7, we divide it into 35, and we get 5. So back in 3rd grade, we get a remainder of 0, and we know that both 7 and 5 are factors of this number 35. So we're doing almost the exact same thing, except here we're using functions. So we know that x minus 1 is a factor. We want to find that other factor, like we did here using division. So let's go ahead and do this. So we're going to go take our polynomial function p of x and divide it by this new factor we just found, which is x minus 1. So we're going to divide x minus 1 into x cubed minus 6x squared plus 11x minus 6. Okay, so we're pros at this now. So we're going to go ahead and we're going to take x cubed, we're going to divide it by x. That's going to give us x squared. So we'll put the x squared up here, and we'll go ahead and we'll distribute that through into our divisor. So that's going to give us minus x squared and then x cubed. We'll subtract these two terms. That's going to zero out. If we subtract the negative x squared from negative 6x squared, that's going to give us minus 5x squared. We bring down the plus 11x, and we start the process over again. So now we'll go ahead and we'll take the minus 5x squared, the lead term of our new line, and divide it by the lead term of our divisor, which in this case is x. This is going to simplify to minus 5x. So we put the minus 5x up top, and we distribute it through. Minus 5x times minus 1 is going to give us positive 5x. Minus 5x times x will give us minus 5x squared. Plus, we subtract this through. First terms cancel out, and this is going to give us a positive 6x. And then the last thing that we're going to do here is we're going to bring down this minus 6, and let's see if we can carry this out. So our next move would be to see if we can actually get another term here. So we would want to take this 6x and divide it by x. So the powers of x are, in this case, equal, so we can still continue on with this, and that's going to give us a positive 6. So we put our plus 6 up here, and we distribute through. So we get a minus 6. 6 times x is 6x. We subtract, we get those cancel out, goes cancel out, and we get 0. This is our remainder. Now we would have expected this because we knew that x minus 1 was a factor, so we wouldn't be getting just some other remainder. Just like we did over here, we know that since 7 goes into 35 evenly, since it's a factor, we wouldn't expect to get a remainder left over. So what we've determined at this point is we've gotten our quotient. So a conclusion that we can draw is that x squared minus 5x plus 6 is also a factor. of p of x. So let's see, in part C we're asked to factor this completely, our function p of x. So x cubed minus 6x squared plus 11x minus 6, this is our p of x, is going to be equal to x minus 1 times this new factor that we found, x squared minus 5x plus 6. Now notice this is the same format that we've been doing in that first problem. You know, this is our p of x, this is our d of x, this is our q of x, and we don't have an r of x because our remainder r of x was actually 0. So this is just like what we did with polynomial division, except we don't have a remainder. So we've just got a nice little factored pair left here. But given that we're asked to factor p of x completely, we notice that q of x here is a quadratic. And we could either look to see if we can factor it by trial and error, we could try and find the zeros using the quadratic formula. However we get there, we can actually break q of x down in factored form further. So we're going to go ahead and we're going to write this completely factored as x minus 1. And x squared minus 5x plus 6 would factor as x minus 2 times x minus 3. So that gives us the complete factored form of p of x. So taking this, we can solve part D. With this complete factored form, we can find the zeros of p of x, because we know that if we're trying to find zeros of a function, we would take p of x, set it equal to 0, and then we just go ahead and solve for x. We also know that given a factor x minus c, c would be a 0, the number that we're subtracting from x as a factor. However we want to think about it, we can go back to this one and we can say via the zero product property, if we know that x minus 1 times x minus 2 times x minus 3 is equal to 0, solving for these, one of these factors has to be 0. That's the only way that this would work out. So this implies that either x minus 1 is equal to 0, x minus 2 is equal to 0, or the factor x minus 3 is equal to 0. Taking into consideration these three possibilities, we know that the possible zeros of this function p of x would have to be x equals 1, x equals 2, or x equals 3. So that takes care of that one. So through this whole process of polynomial division and completely factoring, we found all the zeros of this cubic polynomial. Okay, so that should do it for this one, and I will see you all in the next video.